Okay, Jenny and Sophia showed up here and they asked me to show them how to work out this problem. Problem 33 on page 104, and I understand a lot of people are struggling with this one. So let's do it. Problem 33 on page 104. Here it is. So we've got a train, and it slows down as it rounds a sharp horizontal turn, slowing from 90 kilometers per hour to 50 kilometers per hour. I hate kilometers per hour. In 15 seconds that it takes to round the bend. The radius of the curvature is 150 meters. Compute the acceleration at the moment the train reaches 50 kilometers per hour. Assume it continues to slow down at the same rate at the same time. So here we've got trains. Let's just look down on a train, and so we've got a radius of curvature like this. And what was the radius of that curvature? 150 meters. So we'll say R equals 150 meters. And what's happening is we've got a train, maybe that's coming along. Let's draw the train tracks. And maybe it's straight, and then it reaches this turn, and it goes around this turn, and then it's going to come off the turn, in a different direction, right? But while it's in this turn, it's in a kind of circular motion. It's not uniform circular motion because it's slowing down as it's going around in the turn. So let's, I'm recording right now. What can I do for you? Real quick.
Do you know where Mr. Kinney is?
No. I don't know where Mr. Kinney is, sorry. All right, let's continue. This happens all the time. All right, so it starts off going 90 kilometers. So let's say that its initial velocity right here is 90 kilometers per hour. And right over in here, its final velocity, let's say it's still turning though, right? It says compute the acceleration at the moment the train reaches, so let's put it right here. So it's still turning, but its final velocity here is 50 kilometers per hour. Okay? And so you're braking, but you're also turning. So you have two kinds of acceleration here. You have an acceleration, a component of the acceleration that's slowing it down. That's a tangential acceleration. And it also is changing its direction, so it has a centripetal acceleration. So I'm just going to sketch those accelerations here. Here's the tangential acceleration, and here will be the centripetal or radial acceleration. We'll draw it like that. Okay. And how long does it take to go from here around to here? It's braking for 15 seconds. So we'll just say t equals 15 seconds at that final velocity. So that's everything that's given. It's kind of messy, but what we want to find is compute the acceleration. So we want the overall acceleration, A. Okay, now you probably tried to compute this a sub t and a sub r. Did you do that? Okay, let's see how that went. Let's solve. Let's figure out the tangential acceleration first. That's going to be delta v over delta t. We can say that because it said it's a uniform acceleration. That is, the acceleration is a constant. So this average acceleration is the same as the instantaneous acceleration. And v final is 50 kilometers per hour minus 90 kilometers per hour over 15 seconds. So a sub t. So 50 minus 90. It's now the negative just means it opposes the direction of our velocity. So we can drop the negative, but 50 minus 90 is 40. 40 kilometers per hour. We still have to divide it by 15 seconds, but let's do the unit conversion here. This is 40 kilometers per hour. In 1 kilometer, there's 1,000 meters. And in 1 hour, there's 3,600 seconds. Is that right? And then we're going to take all that and divide it by 15 seconds. And that gives us a tangential acceleration that's equal to, well, let's see, it's 40 divided by 3.6. So it's going to be a little over 10. So it's going to be less than 1, I think. What do you get? Here, I'll race you. See, 40 times 1,000. Was it 0.74? I think that sounds about right to me. 0.74 meters per second squared. That's the tangential acceleration. Now, at this instant in time, we want the radial acceleration, and its magnitude is v squared over r. But of course, this is 50 kilometers per hour. And I think that's, well, 1,000 over 3. Let's just go 1,000 over 3,600. And that will change this to meters per second. And then we're going to square that. And then we're going to divide it by the radius, which is 150 meters. And so when we do that, let's go, see, 50, so 50 divided by 3.6, right, equals, and then we have to square that. And then you divide that by 150. And what'd you get, 1.286? Okay. 1.286 meters per second squared. So here's my tangential and here's my radial. Now if I want my overall acceleration, remember these are at 90 degrees to each other. So I'm going to add the tangential acceleration to my radial, and so my overall acceleration is going to be back where it's like this. So I'm going to use the Pythagorean theorem. It's the tangential squared plus the radial squared. Take square root. So this is going to be 0.74 meters per second squared plus 1.286 meters per second squared. And so my acceleration is, let's see, 0.74 and then I'm going to add to that 1.286 squared, and that equals, and then I'm going to take the square root of that. Oh, where's my answer button on here?
1.48.
Is it 1.48? Okay. Meters per second squared. Oh, there's the answer button. All right. Now let's see if that's right. Is that right? This is chapter 4. Oh, yeah, you can do that. So this is number 33. And it says 1.48 meters per second squared. Good. Now, they figured out that it's 29.9 degrees backwards. So I think what they did is they figured out that angle right here. And that angle is just going to be the inverse tangent of the radial. This is your y, or your opposite is your radial acceleration, which is 1.286 meters per second squared, divided by your tangential acceleration. Is this going to turn out to be 29.9? Usually the opposite has to, well, let me see, inverse tangent of 1.286 divided by 0.74, And that gives you 60.1. Now, what did I do wrong here? I want that, and that's my, if I want this angle here, it's the opposite over the adjacent. The opposite is the radial. So, So the radial is, well okay, hold on a second. This is the radial right here. This is the tangential. It's going to be quite a bit smaller. So they use that. Okay, they gave 29.9 backwards. I guess that they measured it from here, and I'm measuring it from right here. That's essentially the right answer. It's just where they measured it from is different. But you can see that we can draw a right triangle up there and get the angle from that. Okay? So well, anyway, I guess that's the end of the recording. Bye. That is all.